Let's determine what the electric field is like near an infinite line of charge. Now, what do I mean by line of charge? I mean, if we had a thin wire of some kind, and let's say the whole thing was uniformly charged, I want to know what the electric field is like at some point near the line. Let's say that it's a distance r away from the line. And let's also assume that it's infinitely thin, or very close to infinitely thin. Imagine doing superposition for each of the little pieces of charge that would contribute to the overall field. This point charge here would contribute a field to the right. This charge above would create a field that points down and to the right. And then this charge below would create a symmetrical field that points up and to the right. And this would just keep on going for every little piece of charge in the wire. Hopefully it's clear that the vertical components of this will cancel, and there will remain just one net field that points to the right, that points outward from the wire. And I'll call that E, due to the wire. Okay, so how could we ever solve something like this? Well, one method is through calculus. Calculus can solve a problem like this, but so can Gauss's law. In order to do it with Gauss's law, we have to create our own Gaussian surface. It's a Gaussian surface of our choice, though. The best thing to choose would be a cylinder that surrounds this wire. And we have to think about what kind of flux we expect to get out of each of the surfaces of that cylinder. Our cylinder will have a top and a side, and also a bottom. To get that net flux, we have to get the flux of the top plus the flux of the side plus the flux of the bottom. So we want to be able to argue what the flux of the top is just by looking at the situation. Notice that we reasoned that the field will point directly outward from the sides. And by the symmetry of the situation, this will be true at all points. Since the field isn't pointing up or down, we don't expect any flux to come out the top of this cylinder. So the flux through this surface should be 0. It's because all the field lines are going to point radially outward away from the charges and not up or down. So no field lines will actually cut through that top piece. And the same thing would be true for the bottom. With this in mind, the total electric flux will only be the flux due to the side piece, which will be the field strength due to the wire times the area of the cylinder. Now we have a formula for area of a cylinder. The area is 2 pi r times the height, which in this problem we're going to call it L. Now using Gauss's law, we should set this equal to the charge enclosed divided by epsilon naught. And for this particular situation, we want to use something called the linear charge density. The linear charge density involves the total charge on a line or wire divided by the length of that wire. If we solve, we can find that the charge enclosed then will be equal to lambda times the length. And by plugging this in now, in place of our charge enclosed, we should be able to come up with a formula for the field due to this wire. As we can see, the length of the wire doesn't matter when it comes to the field that's generated. It cancels. We can solve the equation totally for E and we get that. Another way to write it, though, will be 2k lambda over r. So determining the field due to a charged wire will require that we know the linear charge density. That's how many coulombs are on a meter, for example, of the wire. And we can use Coulomb's constant and the distance from that wire. This turns out to be very useful in many practical applications because in many cases we can put charges on a thin conducting wire. And now we can calculate how much field will be generated due to that charged wire.